Okay, welcome back. I just wanted to do a quick video on understanding why limits are important for calculus. If you're an engineer like I am, then I had a real hard time understanding why I needed to know what limits are and how they worked. If you can do a derivation and you can do an integration, that seemed like it was good enough to do calculus, but actually if you go back to it later on, 30 years later, like I am, to go tutor my son, you'll realize that actually limits are really the driving factor and very important. So what do I hope to get through in this video? Just a quick introduction of what understanding you need to have pass your calculus course. Let's see, limits, having a better understanding for limits and why they're so important to calculus. And then understanding that if you understand limits, then it's the first step in understanding the language that your math professor speaks. Math professors and math departments make the tests, and they think it's important, so therefore you as a young engineering hopeful should think it's important too. Okay, some basics about limits. Why does anybody care? Okay, as I said, they are the driving engines for derivatives and integrals. In derivation, the limits are really based on slope, change in y over change in x of a curve. And so you can find that slope at any point along that curve. Finding a slope at a single point means that your change in x goes to 0. Which causes problems, but if you know how to do limits, then you know how to handle something as it goes to 0. All right, in the integration, you're finding the area under a curve over a specific domain in definite integration. You can estimate the area by using rectangles, but you want an infinite number of those rectangles to get the exact answer, so you need your number of rectangles goes to infinity, so you have to be able to deal with that. And then limits come back later. You learn them when you are in your first semester of calculus, and then you think you're done with them when you learn how to do derivations and integration, but they keep coming back in things like series and also area between the curve problems, and especially in volume problems. In volume problems, I found it very useful to use the limit structure in order to figure out what function really needs to be inserted into the integration problem. So we'll get into sections. I do have a video out there for solving volume problems, and you'll see what I mean there. Okay, so really quick, going back to why it's important in derivation. If you look here, you can see up here the change in y, and h is actually the change in x. So this guy goes to 0 as you want to move your 2 points closer and closer together. It approaches 0. So this is the basic structure for a derivation. And this type of structure, I would bet you money that would be on your first exam. And so they're going to give you something and possibly say, what's the original function if your derivation is set up like this using limits. So you should be, if you're familiar enough with it, you should be able to figure it out if you know this structure. So more about that in a later video. Integration and using limits for integration in a definite integral. This is what I mean. A definite integral means it has a starting point and an end point, and you're trying to find the area under the curve for that particular region there. So it's from A to B. And so this is, I actually think they kind of should start with this rather than derivatives, because I think understanding the importance of limits in integration, it was easier for me to wrap my head around why it was important. You have something that's going to an infinite number of rectangles. Right here I represented n as 4, but obviously you want your rectangles to be thinner and thinner, the delta x to be smaller and smaller, and therefore the number of boxes that you have to be approaching infinity. So if you look here, f of x is actually the height at that particular x, the height to reach that curve. And then your delta x is the thickness of the box. So this is actually, and you can calculate what you have to do. There's a I and an asterisk here, meaning that you're not really plugging in x here, you're plugging in I and n, because, well, in the summation you need to have something changing, and that I is incrementing through 1, 2, 3, 4, 5, 6, and so on. So if you keep it in terms of x, then you're going to have nothing changing when I changes. So you need to take care of that. And then your delta x is going to be constant. That's dependent on where your b is and where your a is, and then the number of boxes you have. So if this approaches infinity, this guy is going to approach 0. You're going to have a number over infinity. But you keep it in terms of n. I'll have this in a later video as well, so you'll see what I mean. Anyway, I just show a couple of the steps here. You have to find things in terms of summation of I or I squared or even a constant. And then you can start to replace or cancel out your infinities until you can hopefully get to a real number. Okay, some results that you get when you're dealing with limits. After performing all the algebra that you can to cancel out your offensive terms in the denominator, hopefully you're left with something that where you plug out whatever the number that it's approaching into that equation and you get something that is not infinity or whatever, where your denominator is not equal to 0. And if you get a real number, if you can do that, take it and run, that's your answer. It's kind of silly calling it a limit, but it is what it is. All right, so now if your answer is a number divided by infinity, that goes right to 0, because 10 divided by infinity is essentially 0. And if your answer is 0 divided by 0, then you have a different situation where you could have, using the squeeze theorem, you'll learn that later, you could actually have a real number limit, but it's just at that particular point manifesting itself as a 0 over 0. So hopefully, you have to approach it from the left side of the curve and the right side of the curve at that point. And if you do that, your limit is that number that it gets. So I show it graphically on the next couple slides. So if your number is infinity, you may have a vertical asymptote at that particular point, which could be fine, but you just have to hopefully try to avoid that if you can. And then if there's a discontinuity as x approaches of that value, then your limit may not exist. So graphically, what I mean here is the squeeze theorem, this point on this curve is actually, if you look at it, we're missing this point here. It drops down to 0 over 0 here, but your limit is actually right there, and it's about y equals 3. This guy over here represents a 10, represents a discontinuity. So exactly at that point, you have no limit. But if you do have a limit on the negative side over here, that is 1, and your limit on coming from the positive side is 3. So, and I tried to draw the curves here. If you have a limit at positive infinity, well, I'm showing that you're going to infinity. So if this keeps going up and you can't do an Excel spreadsheet or something or other to show that it's leveling off, then it's probably just an infinite. As x goes to infinity, your limit goes to infinity. Here I've tried to represent on the left side that you have some sort of settling out. If you can settle out, in this case it's settling out at about positive 2, then that's going to be your limit over here. So it's some different flavors that you have to understand. And then algebraic case, I just have a couple quick examples here just to show what I mean. In this case, if you have a normal function over another normal denominator underneath a numerator. And if you factor those out, then you can actually cancel out. In this case, it's x minus 2 in the top and bottom. You cancel those two out, your offending point over here just disappears then. And so that is good. And so then you can actually solve the limit directly, and that you'll see that point falls right where it's supposed to. But if you don't cancel it out, it'll stick out of your graph, if you want to look at it like this. Either way, it's squeeze theorem. They're going to want you to do something like this, where you cancel out if you can. And that's how you're going to get the points and solve for a direct real number. And then I made one small change, same problem, but this time I said x goes to infinity. To see what happens, we can still cancel out algebraically, but you're still going to be wound up. You're going to wind up with infinity minus 3 divided by infinity plus 2. Well, infinity over infinity equals 1. So, and you can see it in the graph too. If you graph it, you can see your graph going up. It approaches 1 and never quite reaches it. So it works out well. So anyway, that's what I have for now. There'll be more videos later because there's complexities when it comes to exponents and natural logs and trig functions as well. They add complexity to this that need to be kind of understood and addressed. So more on that later. Thank you. And by the way, subscribe to the channel so you can see when I post these things. I'm going to try to stay on top of the syllabus and as you work through your semester and get through so you can have something to watch ahead of your syllabus. Anyway, good luck with the course.